Okay, I think I'm recording. Yeah, there's the thing. Okay, so mostly this video is going to detail using ChemDraw and Chem 3D. I tried to do this in class, it didn't work out very well. And there's people watching on camera and not many people there, so because you're quarantined and stuff. So anyway, I'm going to try to do it here. Um, Before I get to that, again, I just want to reiterate: you guys need to read all of my messages all the way through and carefully. I get a lot of questions, basically pertaining to stuff I've emailed you about. And the other is a reminder about Wiley Plus. You guys should be working problems. I just checked the grade book. It looks like everybody sort of jumped on and did chapter one problems, and then chapter two tailed off. Like really, at this point, you should have done most of chapter two. Be well into it anyway, and beginning to work problems in chapter four. I cannot stress enough that working problems is how you get better in organic chemistry. And really, it charts. I mean, I'm going to get questions from people who don't do well on exam one. What can I do? And it's going to turn out you haven't worked problems, and that's all you can do. There is no magic trick. There is no way to just sort of like, oh, there's this one little key, and I can, if I know that, I can sort of extrapolate from everything. Um, there's a lot of simple stuff that goes on there, but you've got to work the problems to put it in your head. Okay, so end of lectures. Now, if you're interested in ChemDraw, watch, you can take a look at my background. This is my office. I'm sorry you guys don't get a chance to come in here. I usually do. I have office hours at the whiteboard. You can see my organic molecules on the board, and pictures of places I've been. So anyway, on with ChemDraw. Let me share my screen. I am going to share screen 3. All right, so hopefully you're seeing this. I actually have done this one time already, and it was an entire Zoom presentation of a blank screen. That was fun. So I'm going to come down here. I'm going to open ChemDraw. There we go. ChemDraw Professional. You can download this in the intro module on the Canvas page. There's information on how to download and install ChemDraw on the computer. Okay, so we can draw a molecule on here. So the interface is basically like the one on Wiley Plus, if you've drawn some molecules there. So what is that molecule? Name that. You can highlight it, and you come up here to structure, and you can ask it to convert the structure to name, and it tells you it's heptane. And then you can start putting stuff on there. 2-methylheptane. Turn that into an alcohol. Now something cool is going to happen. See this R? That's chapter 5. We're going to be there really quick if you want to look ahead. And so really, right, that OH could have been in front of the screen or it could be behind the screen. That R tells you which it is. It's not quite as simple as in front of the screen or behind the screen, but that's, let's put, let's actually draw in our H. All right, and then on the next carbon, we can put a couple of things there. Right, so again, now 2R, 3R is, and again, it's not the front, R does not mean in front of the screen. And that's going to go away now because 2 methyls right, methyls in front, methyls in back. Let's put something there. Let's put an H here. Okay, so there we go. We've got our H in there. I'm going to get rid of the name now. You also see over here there's an analysis window. Tells you the molecular formula. The exact mass is the mass of the molecule. Every isotope were the predominant isotope on Earth, right? So every carbon C12, every H is 1, every O is 16. The molecular weight is if we have an average. So there's a little bit of deuterium in there for the hydrogen. There's about 1% C13. Oxygen's pretty much just 16. Okay, I'm going to get rid of the name. Yeah. Forget the 2R, 3S bit. That goes to the stereochemistry, whether you have a wedge or a dash and which one's there. Right. So it's heptanol because there's 7 carbon chain. There's a methyl on carbon 3. There's an OH on carbon 2. So 2 all and 3 methyl. And again, you get to that, like I'll get rid of that. You can highlight your molecule, go under structure, convert structure to name. So now that's ChemDraw, and again, you guys have played with software all your life. You'll figure this out pretty fast. There's a lot of fun stuff you can do with it. Fun being, pretty pretty broadly interpreted. So let's highlight the molecule. I'm going to Control C, and then I'm going to open this program called Chem 3D. You'll get Chem 3D as well with the Chem Office software. You can actually build molecules. Right, there's a building screen over here. I prefer to draw in ChemDraw and paste in, so I'm going to Control V, paste in, and there's our molecule. And then we can grab the hand there and move it around the screen. Grab this rotate button, and we can tumble it all over. So there's something important you have to do. I'm going to show you, there's a Newman projection. Let's do a Newman looking down the C2-C3 bond. That's the most interesting bond with the OH. Right, so now I'm looking down that bond right there. So the OH is on the front carbon. There's a methyl on the front carbon and an H. Behind that, there's a butyl group, 4-carbon group, an H, and a methyl. I'm going to go up here to calculations, MM2, and just say minimize the energy. Just click run on that. Don't worry about all the stuff. And all that's going to do is just sort of do a real simple calculation. Try to put the atoms sort of where it would be the most stable. Clean up the structure that's imported from ChemDraw. Don't worry about it. But you need to do this if you're going to use the next tool, which I hope works. The next tool is not always super accurate, but it's interesting. So what I want to do, as we're doing in class, right? We're drawing Newmans right now. So it's Thursday, February 11th. On Tuesday, I finished up with Newman projections, looking down bonds and talking about energies. I'm gonna come back to that just a little bit at the beginning of today's class, and then we'll go into cyclohexanes. But this will let you kind of play with that a little more. So I'm looking at drawing a Newman projection down the C2-C3 bond, and then analyzing all the plotting the energy versus the dihedral angle. So you got to select your dihedral angle. There's the select tool, C1. I'm going to hit Shift and then click on C2, C3, and C4. So really, I'm looking at the angle of the C3-C4 bond versus the C1-C2 bond. And now if you go up here again to calculations, dihedral driver, single axis angle plot. Now watch, I want everybody to look carefully at the molecule on the screen when I click single angle plot. Right? So it runs all the way around there like we've been doing in class, only it's a computer, so it can do it faster for one. It can also keep track of things a little better. It doesn't have to do, in class I was doing 60 degrees at a time because it's, what's the energy at 33 degrees? I have no idea. So, but I can tell you if we're staggered and we go 60 degrees to eclipse, cool, that's going to be higher in energy. 60 more degrees to another staggered, we'll be back lower in energy. So you get this plot shown on the screen, energy, and don't worry about the numbers really. Just remember that less stable is higher, more stable is lower. And then you get the dihedral angle. So the highest energy, the least stable this molecule can be in terms of its conformation, is at a dihedral angle of 0 degrees. So click on that spot. And now you see the structure changes, and we can move this around. And look at that. We've got the syn eclipsed conformation at the highest energy, just like I told you in class. Right? So looking down the C2-C3 bond, if the front methyl eclipses that back butyl group, again, the methyl and the butyl are the biggest groups on the front, on the 2 carbons we're looking down. That's a lot of steric interaction. And then you also see, and then usually when you draw this on the board, you'd cant it a little bit. The OH is eclipsing the methyl group, right? So 2 high energy interactions. And you can see why, like these 2 hydrogen atoms are too far apart. The 2 hydrogens on the back and the front carbon are too far apart to really interact. But if you look at this and you can kind of imagine, and again, the ball and stick model is not real useful. Or it's sorry, very useful. It's not real accurate. These atoms all have sort of an electron cloud around them, so they're bigger than they look on the screen. And so you can imagine as this butyl group turns around, as the methyl group spins, that these two groups can, they can physically interact a little bit, as can the methyl and the OH. The bigger the groups are that are eclipsed or gauche, the stronger or the more they interact. So, and that interaction is negative. Okay, so that's the highest energy point. What about this medium energy point? So let's come over here. Now, and if we look down that, it's an eclipse. The three high energy points are all eclipse conformations, right? So here we have methyl eclipsing H, H eclipsing methyl, and then an OH eclipsing the butyl group. And that's, the OH is smaller than a methyl. Let's click on the other one, other eclipsed. Again, so all three high energy points are eclipsed conformations. And we have two methyls eclipsing one another, and that's why this eclipse is a little higher than that. Let's look at the low energy. So the lowest energy, or the dihedral of 180, is just where we were originally, right? Methyl is anti to butyl. We've got a methyl-methyl gauche interaction and an OH-butyl gauche interaction. You want to minimize gauche interactions. Okay, so the lowest energy Newman projections are going to have staggered conformations. And you're going to have three of those. For any alkane, for any carbon-carbon single bond, there's going to be three staggered conformations. And what you want to do is look at those for the low energy conformations, and the ones that have the biggest groups anti and the fewest gauche interactions will be lower in energy. Right, there's three, I said. So here's another staggered conformation at a dihedral angle of 60. So here we're looking down that. Now we have methyl OH gauche, OH butyl gauche, and butyl methyl gauche. So now we have 1, 2, 3 gauche interactions. This low energy at 180, we only have 1, 2 gauche interactions. Right, so having fewer gauche interactions gives you a more stable conformation. The third staggered conformation is here. And again, we have 3 gauche interactions: OH methyl, methyl methyl, methyl gauche. Okay, so anyway, that's ChemDraw, Chem 3D, a little bit about Newman projections. This is if you like drawing molecules and playing around with them, ChemDraw and Chem 3D are a lot of fun. If you hate computers or you hate molecules, you probably won't enjoy this much, but you probably still should do it because well, you should do it if you're having trouble translating what we're drawing on paper and on the board into sort of a 3D model in your head. And when we get to stereochemistry, it'll be a little more useful as well. All right, I'm going to stop sharing my screen. I'm going to check the video and make sure molecules are actually on it instead of just like my background. And I'll see you in class. Not sharing screen. I will now see you in class.